electricity running through a coil makes a magnet, and the little leaf has a magnet on the bottom of it, and when that happens, it repels it. And so it jumps. And so we build up energy, and this thing bounces around. There's a lot going on here for a buck. Okay? I mean, like, you know, you could win a science fair for a buck. Okay? So remember that. Okay? It's a kind of a surprising thing, and, you know, don't pass up dollar stores. So what we would like to do is investigate that charging rate a little bit more in a more focused manner. And so once again, welcome to the world of ancient history at an Ivy League school. I'll bet you don't have meters like this. Okay? So these are two big old demonstration meters. This reads, now we've got a big capacitor here. This is just 2 layers of aluminum foil rolled up with saran wrap between them and put in there. It stores a fair amount of electricity. We've got this set up in a very similar fashion. I can charge this and I can discharge it. And let's have a look at how that goes. Okay, let's get some electricity. So this is going to be a power supply that gives me about 4.5 volts. When I put this on charge, I'm going to run that to the capacitor, and we're going to be able to see the voltage, which is to say how strong are the charged particles in the capacitor, and the current, which is to say how many charged particles are moving. Okay? So let's do that. Here we go with the charge. Lots of current. As the voltage goes up, which is the repulsion effect, the current goes down. But notice that it trails off. It doesn't just zoom up to 0. It moves pretty quickly and then trails off until we finally level off at about 4 volts. So now I've charged this capacitor to 4 volts. Okay? And now it will hold that voltage. I'm going to discharge. I'm going to give it an escape route, and we're going to watch what happens. And what happens is the current goes the other way, and the voltage trails off until with no voltage, there's no push on the charged particles, and they stop moving. Now we can look at that and we can describe it. And the problem with descriptions is that they're subjective. If your grandmother says, you shouldn't ride with your uncle, he drives too fast. You know, are you going to say, well, hell, I'm not going out there with my uncle, he's crazy? Or are you going to say, my grandmother is such a wuss? You know, like, I'm not worried, you know? But if you're at, you know, a celebrity signing thing, and Mario Andretti says, you know, you shouldn't drive with your uncle, he drives too fast. You know, you're going to, he's too fast for Mario Andretti? You know, like, maybe I better not get in that car. And so too fast really is not very descriptive. It really depends on your origin. Okay? What you really need is a number. If your grandmother says, you know, your uncle drives 130 miles an hour on the Schuylkill Expressway, you know, you're going to say 130 miles an hour. Okay, you're not a wuss. You know, like, I don't want to be in that car. You know, and if Mario says it, it's still the same thing. So if we can get some numbers, so that's what we're going to do. And if I'm lucky, okay, we can get a graph. And so what we've done is we've hooked up a recording voltmeter. We're using Vernier Lager Pro for anybody who may have that stuff. Okay. This is a time axis. We've got a 50-second recording time. This is voltage here. So we're essentially going to record the reading of this meter. But now, these are going to be numbers that are not subject to interpretation. And we're going to do all the same things. Okay, so the first thing we want to do is start the graph. So the graph's ticking along and there's no reading, or pretty close to no reading. Okay, and we apply some voltage. It climbs very fast, and just as we thought we observed, it trails off. And this is very interesting stuff. So in 1 second it went up that much, in the next second it went up less, in the next second less, and by now every second it's not changing at all. So let's turn that off, it's leveled off, and now let's discharge it. Same situation. In the first second that we discharged it, look, it dropped almost halfway. in the next second not as much, and now it's not dropping practically at all. A quick, dirty description of a capacitor would be that it's a bucket and that the electricity is water. But this tells us that's not a good model. Because if I was putting water in a bucket, the water entering the bucket doesn't care about any water in the bucket. There is no reason for the later water to come in slower. The water enters the bucket at the same rate all the time. So we may be putting water in the bucket at the rate of 1 gallon a minute. And the first gallon takes a minute to go in, and the last gallon takes a minute to go in. That's not the case here. And this is a critical understanding with electricity. Not only does electric charge get affected by electric fields, it causes electric fields. And so the presence of electricity affects the behavior of later electricity. When we find that the value of a measurement affects the way the measurement changes, we end up with a behavior that we call exponential. Maybe the most famous of those is population. The value of the population determines how fast the population grows. If you have a very small country, they don't have very many babies. If you have a big country, they have lots of babies. Okay? And so population growth is exponential. So we find this is mathematics that explains many, many behaviors. And it's quite interesting to discover that physicists and biologists would want to know this matter. Okay?